Let's try this again. We're going to solve quadratic equations, and we're going to show how this equation represents the flight of the ball. Okay. Now, if we were to quickly graph this, we know the a value is a negative, so we are going to have some quadratic that is facing downwards. Okay. And the very first question is asking us is, when is the ball on the ground? Well, since our x-axis is going to be representing our time, and our y-axis is going to represent height, we know that a ball on the ground is when we're cutting through the x-axis. In other words, when y is 0. Okay? So that same idea, we are going to replace our height with the value of 0. Okay? Negative 2x squared plus 12x. Okay? And what I'm going to do is I want to get my x's isolated. So we're going to factor. And the very first style of factoring we talked about already was common factoring. There's a common factor of negative 2x involved in all of these. Okay? So we're going to take negative 2x out of each of these as a common factor. We'll have 0 is equal to negative 2x. What will we have left over? Not plus. Minus 6. Okay, good. So, at this point here, this is actually as far as we can go with factoring. And I know many of you guys run into trouble with this here. That's why I chose this specific example. We have negative 2x multiplied by x minus 6 is equal to 0. I want you guys to still think of this as specifically a term. So put like dotted brackets around it. Multiplied by another term. In order to create a 0, one of these terms has to be equal to 0. So we could split the equation again from here. When we split it, 0 will be equal to negative 2x, and 0 will be equal to x minus 6. To isolate x, what will we do? We divide by negative 2 because it's multiplied by. And what is 0 divided by negative 2? 0. So one of our x values is 0. And when we move 6 to the other side, we're going to get a positive value of 6. So we get x is equal to 6. So we've just discovered that our x-intercepts, when we make a rough sketch of this, one of them is at 0, the other one is at the value of 6. Because we knew this face downwards, that is when our ball hits the ground. So let's try to make sense of this, and I'm going to make that a little clearer because it's very ugly looking. But let's try to make sense of what that means in terms of the flight path of a ball. Okay? So when time was 0, the height was 0. In other words, what does that mean? The ball's on the ground. Right after that point, what happens to the ball? Does it drop or does it go up? Well, depending if we're throwing or kicking or whatever it is, if this is modeling the flight path of something, from this point it looks like it is going upwards, it reaches a peak, and then comes back down, and finally hits the ground after, and we'll say our x was in seconds, after 6 seconds. It hits the ground. So at 0 seconds it starts on the ground, so maybe we were kicking it. If we were throwing it, it would probably be above the ground in our hand, right? So we're kicking this ball. It goes up, and after 6 seconds, it comes back down to the ground. That is excellent hang time. So what is the maximum height of the ball? How can we use this information to help us solve what the maximum height of the ball is? What part of the parabola would be considered max? The vertex. How can we find the vertex when we have two x-intercepts? What's that equation? AOS. What's that stand for? Axis of symmetry. So, we're going to take our two x-intercepts, R and S, and we're going to divide them by 2, which means we have 0 plus 6 divided by 2. 6 divided by 2 is equal to 3. The axis of symmetry, or the time when the ball is at its max peak, is at 3 seconds. So we've just solved for the x value of the vertex. Okay, we're still looking for the y. To find the y, we need to plug back into either our standard or our factored form of the equation. Okay? Last time we did this, we did the standard form, so I'm going to plug it into the factored form just to show you that it can be done. Our factored form of the equation, after we common factored, was the height of the ball is equal to negative 2x, x minus 6. We're going to look for at 3 seconds what the height of the ball is. Okay? That means we're going to take values and plug them in for x, specifically the value of 3. So, we plug in 3 for x. In both of the equations. We deal with bedmass first. 3 subtract 6 will give us negative 3. And then 2 times positive 3 will give us negative 6. Negative 6 by negative 3 is 18. So the y value, or the height of this ball, say it is in meters, the height of the ball was 18 meters, the max height. At 3 seconds, it got 18 meters into the air, and then at 6 seconds, it finally hits the ground again. Okay? So that's using the stuff and information we used from our last lesson to model the flight of an object.